So simplifying exponents and radicals. Review. Okay. So first of all, let's look at the first rule on here. A to the 0 power. That's not an O like the letter O. It's the number 0. Guess what A to the 0 power is? 1. Okay. Now this works as long as A is not 0. A can't be 0. 0 to the 0 power could be 1, but it could be infinity, or it could be 7, or it could be a can of peaches. You don't know. We call that indeterminate form. But any other number besides 0 to the first power or to the 0 power is what? 1. So it's 5 to the 0. 1. What's a fifth to the 0? Good. Anything to the 0 power is 1 except 0. It could be 0, but it could be infinity, or it could be 7, or it could be a can of peaches. It's called indeterminate form. You'll learn about that if you go on to take calculus, okay? It could be, it's something that is, it's like 0 divided by 0. It's like dividing by 0, right? It's something, okay? But it could be 0. We just don't know. It could be 1. It could be 7. It could be a can of peaches. Here's my question. Why? Why is anything to the 0 power 1? Who made that rule? Well, it's because of this rule right here. Let's come down to this line here. We reviewed this yesterday. A to the m divided by a to the n. When you're dividing and the bases are the same, what do you do with the exponents? You subtract them. It's a to the m minus n. Okay? So here's why this rule at the top has to work. What's 4 divided by 4, everybody? 1. You know that, right? Well, can I use this rule of exponents? This is 4 to the first over 4 to the first. Aren't the bases the same? Yep, so I can use the rule. It would be the top exponent minus the bottom exponent, which gives us what? 4 to the 0. What's 4 to the 0 power? 1. Why is 4 to the 0 power 1? Because 4 divided by 4 is what? 1. So why cannot a be 0? Because if a to the 0 works for any number but 0, because that number divided by itself is 1, what's 0 divided by 0? Caden, what's 0 divided by 0? Can't do it, right? It's another indeterminate form. It could be 1, could be 7, could be a can of peaches. We don't know, okay? So that's why 0 to the 0 is indeterminate. All right, so that's cool. Anything to the 0 is 1. When you're dividing and the bases are the same, you subtract. What do we do when we're multiplying and the bases are the same? What do we do with the exponents? We don't eve them, we add them, right? Add them and eve them. We just add them. All right, we saw this yesterday. If you have multiple factors, this is being multiplied. Being multiplied. What can you do if you have an entire set of factors raised to a power? You can put little exponents on the ones that aren't there. And of course, if they're not there, they're implied to be ones, right? So I'm going to put a 1 on there. And we distribute. We multiply. When you raise a power to a power, you multiply. And every factor's exponent is going to get multiplied. So it would become a to the 1 times n, which is a to the n, times a to the m times n, which is mn. Okay? Here's an example of it. Oh, no, there's no example of that. Let's try it out. Example. Let's try 2x to the 3rd, y to the 7th, all to the 3rd power. What's that going to be? What happens to the 2? Does it become a 6? No, because we're multiplying not the base, we're multiplying the exponent, which is 1. So it becomes 2 to the what? 2 to the 3rd, 2 to the 3rd, x to the what? 9th, y to the 21st. Now we can simplify that because we know 2 to the 3rd is what? 8. Yeah. So that's what that becomes. Okay? All right. When you raise the power to a power, you multiply. Now, here's what does not work. This is a big time no. If you have a plus b to the m to the nth power, does that equal a to the n plus b to the m times n? No. What's the difference? This is being added or subtracted. That does not work. If you're trying to expand sums, you have to FOIL it out or do something quite elaborate. But if it's one term, Terms are separated by plus or minus signs. If it's one term and you have multiple factors, then you could just distribute that all the way through. Now, it doesn't matter if they're being multiplied or divided. Let's come up here and look at another example. What if I have this? What if I have 2x squared y cubed all over z to the fourth, and I'm raising all that to the fifth power? Is that one term? Do you see any plus or minus signs on the inside? I don't. So it's one big term, and we have four factor groups, the 2, the x, the y, and the z. It's all raised to the fifth power. Guess what we do with the 5 to all the exponents? We distribute it. So it becomes what? The number becomes 10? Is that right? No, it becomes 2 to the fifth. What's another name for 2 to the fifth? 32. There it is again. And then we get x to the 10th, y to the 15th, all over z to the 20th. There we go. Now we're cooking. Do all of these rules work with fractional exponents and negative exponents as well? Shake your head up and down like yes. Yes, they do. They absolutely do. The rules of exponents work for all types of exponents. Okay, here's that rule that I just taught you. A to the negative m is the same as 1 over a to the m. Okay? So just to have a thorough list here, 1 over x is the same as x to the negative first. 1 over x squared is x to the negative second. 1 over the square root of x is x to the negative 1/2. And you can keep, we'll do one more. 1 over the cube root of x is x to the negative 1/3. And I'll do that other one I did. What's 1 over x to the negative fifth? What do we say? 1 over x to the negative fifth is just x to the fifth. Yeah, it doesn't matter where the negative exponent is, top or bottom or whatever. As long as they're being multiplied, you can't have plus or minuses in between the terms. As long as it's one term, you can bring the factor from top to bottom or bottom to top, as long as you change the sign of the exponent. Okay? And the reason that that is like that is because of the subtraction rule again. If you have more factors in the bottom than in the top, you end up with a negative number when you do that rule. And that means that you have more left over in the place where there was. All right, so you can read all these if you want, but we did some examples. Let's try it out. Example 1, the instructions are going to be to simplify. How many terms do you see? One term, right? One term. There is no plus or minus sign. So these are all factors. A 1/3, an x squared, a 12, and an x to the fourth. I have four factors that are separated by either a space or a dot, which means multiplication. Now, we can combine like factors. Did you know that? We can combine like factors. So let's do the numbers first. What's 1/3 times 12? That's 4. What property allows us to multiply those two together even though they're not sitting side by side? Y'all remember? What property of multiplication allows us to associate factors together that aren't written side by side? It allows us to associate them together? Close. The associative. Yeah. Isn't the associate? That's the name of a band, the association. The associative property. We can associate or group those together even though they're not side by side. We can do the same thing with the x. What's x squared times x to the fourth? What do we do with the exponents when the bases are the same and we're multiplying? We add them. What's 2 plus 4? 6. So that simplifies to 4x to the 6th. Okay. Number 2. Whoa, boy. Now I have two factor groups. Okay. This big group squared times this big group cubed. Your goal is to tear down walls. Your goal is to get rid of parentheses. If you can get rid of parentheses, you can start combining like factors. So to get rid of the parentheses, I have to distribute the 2, and I have to distribute the 3. Now, here's what I recommend everybody does. Here's what I see as a common error. I see people, they know they have to multiply, so they make the mistake and say 2 times 5 is 10. That's not what we're doing. So what I like to do is if there is not an exponent showing, I put a little 1 there to give myself a target. Okay? So now I can distribute the 2 by multiplying to both of those, and I get 5 to the second times x to the negative second, and I tore down the walls. I don't need the parentheses anymore. And then I do the same thing in the second. 3 times 1 is 3, so I get 2 to the third, times 3 is 9. I tore down the walls, Gorbachev. All right, now I can combine like factors, but there's still something to do in the PEMDAS. I have 5 squared on my number and 2 to the third on my number. I can simplify that. That's 25, x to the negative second, times 8, x to the ninth. Now we can do what we did on the previous problem. We can combine like factors together. What's 25 times 8? If you have 8 quarters, how much money do you have? You have 200 pennies, right? And then what do I do with these two exponents? Because the bases are the same and I'm multiplying, I add them. What's negative 2 plus 9? 7. So it's 200x to the 7th. Inch by inch, it's a cinch, right? Inch by inch, it's a cinch. Line by line, just one little piece, one little piece. Okay, so far so good. That was a good one. Just kidding. I like the way you kid around. No, you answered your question, though? You figured, okay. Any other questions before we move on? Muy importante. And of course, all of this stuff that we're doing works with negative exponents, obviously. We see one. And it also works with fractional or rational exponents. Okay, letter 3. Boo, boo, boo. How many terms do you see? I see one term. I don't see any addition symbols or subtraction symbols. It's one big term. I have 4 factors in the numerator and 4 factors in the denominator. I can combine like factors, okay, using the rules. Now, numbers are always a little bit different. So, if you were to simplify just the fraction 3/6, what would that simplify down to? 1/2, right? So I'm going to go ahead and write that as a 1/2. Now, for the letters, I can combine them using, since I'm dividing, I'll use this rule right here. When I'm dividing and the bases are the same, what do? Subtract the exponent. So let's go ahead and do that one by one. I have x to the, what's 5 minus negative 2? Ah, gotcha. 5 minus negative 2. It's a mental mistake that a lot of people make, Riley, including me. Good, it's 7. If we say 5 minus negative 2, you know what your brain does? Your brain automatically says, I know we're subtracting the bottom number, but hey, there's already a negative there. How convenient. And so we end up saying 5 minus 2, which is what? 3. Well, 5 minus 2 is 3. It's the wrong answer. Okay? So we got to remember, if we're subtracting the negative, we're really adding. So what's 5 minus negative 2? It's 5 plus 2, which is 7. I didn't mean to call you out, Riley, but I do the same thing very often as well. And I'm glad you did that. I asked Riley before class to shout out 3. Yeah, perfect. She was right on cue. All right, what do we get now? Y to the what? 2 minus 2 is 0. I'm going to go ahead and put it in there for inventory purposes. Inventory. And then z to the what? 4 minus 6 is negative 2. Yeah. Okay, now, is it completely simplified? It's not completely simplified. There's one more thing that I would consider doing. What do we know y to the 0 is really equal to? 1. So I would say x to the 7, z to the negative second. Now, in pre-cal and calculus, that would be a perfectly fine answer. We work with negative exponents routinely. But let's get in the habit of figuring out how we could get rid of negative exponents. Having a negative exponent or a fractional exponent in your final answer is kind of undesirable. So, what is this actually equal to? Well, if I think about z to the negative second off to the side, that's equal to what by itself? 1 over z to the what? Positive second, right? That's what negative exponents do. So z to the negative second, if you want to put this over 1, you can. We just bring that factor to the bottom and change the sign of the exponent. Well, if I bring it to the bottom, there's a 2 in the bottom. So now I can write it like this, one big division bar. I'm going to have x to the 7th in the top and z squared in the bottom with the 2. That's another way to write it. These two are really the same. Of course, there's a 1 in the top, but we don't need to write the 1. You see that? The 2 didn't need to be written in the bottom of the whole thing because it was just a number. Now, you could have said it was x to the 7th, z to the negative 2 all over 2. That would work as well. But since this is going to the bottom, might as well give them a friend down there, right? Isn't it nice to have a friend? I wouldn't know. All right, questions? The 2? I got the 2 from the bottom by doing this. Z to the 4th divided by z to the 6th. When the bases are the same, we subtract. So what's 4 minus 6? No, it's negative 2. Oh, yeah. It's negative 2. Now, because there's a negative 2 in the top, it becomes a positive 2 in the bottom. Okay, that's the new rule. I can't believe you haven't had negative exponents. I don't know where you would have seen them. Aisle 5 at HEB, maybe? No, there's no negative exponents there. Algebra 1, you never covered them in Algebra 1, negative exponents? And they haven't come up this year at all, huh? Okay. All right. Now we know what negative exponents are. All right, let's do radicals. Combine if possible. Factor tree groups come out. Rangers there. Okay. Reviewing simplifying radicals. If we have a radical number, we first look to see what the radical is. It's the square root, right? So I can write this number as 180 to the 1/2 power, right? 180 to the 1/2 power. I don't want to write it as 180 to the 1/2 power because, again, we don't think in terms of fractional exponents just yet. They're new. So I'd rather have it as the square root of 180. I know how to take the square root of a number. Now, is 180 a perfect square? No, it's not. It's not. Now, is there hope for numbers that aren't perfect square to be simplified? Yes, if they have a perfect square factor, you can simplify. The way to do that is to do upside down birthday cake or factor tree, which I know we've done this year already. So let's do it. Someone give me 2 factors that multiply to give me 180. Any 2. 2 and 90. Dang, I thought you were going to say 18 and 10. But I can't predict you. You're unpredictable. And then 90? Whoa! 45 and 2. I thought you were going to say 9 and 10. I'll do 2 and 45. And then 45. I'm interested to see what you're going to say. 90 and a half? What? Oh, 9. Okay, 5 and 9. And then 9 is 3 times 3. And there's the prime factorization right there. There's the prime factorization. Now, remember what we said earlier in the year. The root index, or the root, or just the index, whichever one you call it, is the price for freedom. It's the price of freedom. Think of these numbers as being caged or imprisoned underneath the radical. They don't realize they can just walk out the right-hand side. It's open, but don't tell them. They're caged inside the radical, and they want to get out. The root index here is implied to be a 2. Yes, yes? So remember, and we've done this before, it takes a pair of factors on the inside to become one of them on the outside. So I can pull a pair of 2's out and call it 1, 2. I can pull a pair of 3's out and call it 3. And then anything that's left is stuck on the inside. And then I just multiply and get 6 square root of 5. So apparently 180 is 36 times 5. Yeah. And 36 is the perfect square. Remember doing that? Yeah, okay. That's kind of easy. Letter B. Well, what if I have radicals now that have also variables? Well, treat it as 2 separate problems. 2 separate problems. Okay, I can actually write this as the square root of 56 times the square root of x cubed y to the 6. Okay, that's the property of radicals and exponents that we could do. So 2 separate problems now. So off to the side, I write 56 and I get the factor tree. By the way, off to the side, do I write the square root of 56 and then do the factor tree, or just 56? Just 56, not the square root. We're trying to figure out the square root of 56 by looking at 2 factors. Okay, the factor tree of 56. 7 times 8 or 9? 8, yeah, okay. That's where the times tables get a little squirrely in there, right? 7 times 8. And seven's prime, and then 8 becomes 2 times 4, and 4 is 2 times 2. So that should work, right? So now I look for my pairs, and I have a pair of 2's right there. Just one pair of 2's. So on the number, I can bring out 1, 2, and then what's left on the inside? A 7 and a 2, which multiply together to give us what? 14. Yeah, so 56 is apparently 4 times 14, and 4 is the perfect square factor. So I got the number down. Now, here's what we do for the variables. For the variables, it's actually easier to simplify when the radical is written as a fractional or rational exponent, okay? So let's see if we could do this in one step. The whole thing is under a square root, yes, yes? So it would be the whole thing to the what power? Hang in there, David. It's not that bad. If it's a square root, it would be the whole thing to the 1/2 power. 1/2, right? If it's a square root, it becomes 1/2. And then I would take the 1/2 and distribute it to both of those, wouldn't I? So let's see if I could do those two steps in one step. Since they're both under the square root, they both get the 1/2 power. So it's x cubed to the 1/2 power times y to the 6 to the 1/2 power. Are you okay with me doing that? We did two things in one. I brought you along for the ride, two things in one. Now, here's what we can do from there. I can simplify by doing what with these? When you raise a power to a power, you what multiply? Multiply. So working straight down, I get 2 square root of 14 times x to the what power? 3 over 2 power times y to the 6 over 2, which actually simplifies to 3. 3. So this could be your final answer. Final answer, we'll call it version 1. You can have multiple versions. Now, let's do this. Since it started as a radical, let's go ahead and put the x to the 3/2 back in radical form. What would x to the 3/2 be back in radical form? Square root of x to the 3rd. Good, good. So this is final answer version number 2. Final answer version number 2. Now, isn't it nice to have a friend, I said earlier? Yeah. The 14 and the x cubed are currently being imprisoned separately. They're being imprisoned separately by the same prison, right? They're both square roots, and they're being multiplied. So guess what we could do? We could throw them in the same prison cell. They don't need separate cells. Let's put them together. So that would be 14 x cubed times y cubed. This would be final answer version number 3.
Are all of them correct?
Yeah. Yeah. On a free response, yeah. Why do I go through all final versions? Because if it's a multiple choice question, now you have to match your answer up to the right one. And any one of those answers could be an answer choice. Got it? That's why we test you in two formats. Multiple choice, you got to match it up. Free response, you can stop at any one of those. Yes?
Is the y cubed under the radical?
No. Does it look like it's under the radical? No, I'm being serious.
I'm not the one who asked.
No, I'm being serious. This is a great question. Notice how my radical stops short of the y cubed. That's very deliberate. That's very, very intense. I wasn't making fun of you. I'm saying that was a fantastic question. Because if you write it like this, and you stop your radical short of the y cubed, I'm going to interpret the y cubed as being on the outside. Now, what if the y cubed was actually supposed to be under the radical, and you wrote it like this? Are you getting credit? No, you better cover exactly what needs to be covered. So some people are real careless. Some people are real careless with their radicals. Oh, because 6 to the 1/2 ended up being an integer. I can put it back under the radical as long as I call it y to the 6. But because 6 times a half is 3, I don't need to put it under the radical. That was a question on the test where the final answer was the cube root of x minus 2 all over 3. That was one of the answers on the test. And a lot of people lost credit because they did this. They did x minus 2 over 3, and then they did their radical like this. If you were grading that, would you count it right if this was the right answer? No, because look how the radical extends below the division bar. See that, first of all? But not all the way to the bottom of the 3. So the 3's butt is kind of hanging out the bottom. See that? Half of it it's in, its head is in there, but its butt is hanging out. What do you do when its butt is hanging out and its head is in there? I'm assuming that it's in there, so you'd not get credit for that. So if you wanted to make sure that was outside, what you would need to do is what? Would separating it like this help? Would you call that 3 on the outside now? The answer is no. No, it's still not on the outside. How do you make sure you know it's on the outside? You make the line longer so that the cube root is in the numerator and the 3 is in the what? Denominator. Some people just put a 1/3 out front. That's más mejor que bueno. Okay? Details matter. Yeah. Yeah.
When we draw the square root, can we bring it down a little bit so it ends behind the exponent? Or is that
So the what?
when we draw the square root?
Here, draw the square root. What are you asking?
So you were using like this.
Uh-huh. Yeah, yeah.
X, and like say it's like minus.
Sure.
Can we do it like that so you know it's here and then like whatever our number is?
Oh, I like that. Yeah. There's no reason why we can't modify the notation slightly because the whole goal of the notation is to communicate. She asked if we can put a little return box up here to show that it's cut off instead of just leaving it hanging. That would have answered your question, right? Yeah, that's fine. So I like that actually. So where did you? Oh yeah. So if I would have done this right here, if I would have put like a little down box right there, now you would have known what that the y cubed is specific on the outside. I like that. I'll take that to the next math seminar and I'll present that and we'll see if we can't get that into every high school in America. Okay? That's not bad. I like that idea. Sure.
Wait, why do you not need like the multiplication sign that's so wide?
What now?
You don't have multiplication on the last one.
Why do we not need multiplication on this one? Why do we not put a dot right there? Oh, because it's implied. It's implied. Like if I did x cubed y, would I need a multiplication symbol in between them? No, it's implied to be a multiplication symbol. Yeah. The only time we need to make sure we have the multiplication symbol is if I did 2 times 3. Can I write 2 times 3 side by side like that and think, hey, that's multiplication? No, that's the number 23. Oh, I was raised in a barn by a chicken. I don't know anything. Yeah, if I put a dot there. But variables, like if I put 2x, now we know that that's multiplication. If it's two variables, I know that's multiplication. Same thing with the end of the radical. When the radical ends, what follows behind it is multiplication. Now, Lauren, is it okay to put a dot there if we want to make sure it's multiplication? Yes, we can. The whole goal is to communicate. But on the other end of that spectrum, mathematicians like to be as efficient as possible. So if we can get by without making a parenthesis, we're going to try and draw without a parenthesis. If we can get by without making a dot, we're going to try and draw without a dot. But again, add stuff there to make sure that your answer is very, very clearly communicated without you standing there saying, this is what I meant. The work has to stand on its own. All right, last one, number 6. I have 2 factor groups. Okay, whoa, I wanted the highlighter that time, and look what I did. Stupid pencil. I don't say that very often. Okay, we have this group, and then I have this group. My goal is to get things together. I want to be the Nelson Mandela, the Martin Luther King of these problems. I want to bring things together in harmony. I have numbers, and I have m's, and it's all one term, so they're all factors. So you can think of radicals like being parentheses. I need to tear down the radicals. I need to tear down the parentheses. Well, the first step is to do what with the radicals, do you think? Step 1, get rid of the radicals. Get rid of the radicals. Okay? It's like if you just established a new country, what's the first thing you're going to do in your new country? You're going to get rid of the radicals, right? Because they just breed discontent and dissent. No, you need radicals. You need differing opinions. So this is going to be 14m to the what power? 1/2. Times 3 is outside the radical, times the quantity, 2m cubed to the what power? 1/2 power. Yeah. Now we're back to the previous problem where we have to tear down that wall. So I'm going to put little 1s right here, and I'm going to put a 1 right there. And now I distribute like this. So I get 14 to the 1/2, m to the 1/2, and I can get rid of the parentheses. And I'm putting a dot here for clarification. Um, Usually, if I put like 3m to answer Lauren's question, 3m implies multiplication. The commutative property says I can write it like that. But if we put m3, that just doesn't look right, does it? M3 looks like a company name or something. So that's where we typically, if it's M3, we would put a dot to show that it's multiplication. But we technically wouldn't need one. Okay? But I'm using the dot here still to show the separation between the two groups. Now I multiply this one, and I get times 2 to the 1/2, m to the 3/2. Inch by inch, it's a cinch, baby. All right, now I can simplify. Let's do our numbers first. 14 to the 1/2, that's the same thing as the square root of 14. Is the square root of 14 7? No, that's 14 times a half. We've got to be careful. 14 is not a perfect square, is it? No. What about 2 to the 1/2? Is that a perfect square? The square root of 2? Is that, But you know what we could do? Since they're both to the 1/2, look off to the side here on your workbench. Okay, here's your workbench. I want you to see it. 14 to the 1/2 times 2 to the 1/2. I can associate those two together, even though they're not written side by side. By what property? I can associate those two together. Associative. Yeah. Now, because they're both to the 1/2, they're both under the square root. And like I said earlier, because they're both in the same prison, they're both square root prisons, not cube root prisons. They're both square root. I can imprison them in the same cell. And now I can multiply. What's 14 times 2? 28. Is 28 a perfect square? Please say yes. No, it's not. No, it's not. But thank you for abiding. It's not a perfect square. Do I know how to see if it has a perfect square factor? Yes. 2 times 8. Anana, what you got? Are you doing 1 times 28 or are you doing 2 times 14? Are you doing 7 times 4? I'm going to do 7 times 4, and 4 is 2 times 2. There's a pair of 2s. So I can get rid of this and call both of those combined 2 square root of 7. Are you okay with that? Is it okay to go off to the side and use a workbench before you bring it back into the project? The project is working straight down. All right, now, I have one other number, don't I? I have a 3. I'm just going to bring him along. He hasn't done anything yet. He was just watching those guys. What are you radicals doing? Shut up, 3. Okay. So we just rewrite it. Now, let's look at the m's. I got some m's. M to the 1/2 times m to the 3/2. What do I do with the exponents when the bases are the same? I add them. Let's do this together. What is 1/2 plus 3/2? 4/2. What's another name for 4/2? 2. 2. Those add up to 2. So that becomes squared. And I think there's one last thing we can do. There's a 2 times a 3. They're both outside the prison, so we can multiply them together. If there was another radical, we can multiply those together under the radical in the same prison. What's another name for 2 times 3? 6. What property allows us to associate those two together, even though they're not written side by side? Associative property. So that's 6 squared root of 7, m squared. And now in the end, I have one representative number, 6 square root of 7, and one representative m squared. And that's what we should do. If there's a bunch of numbers and a bunch of m's, at the end we should have one number and one m. We combine them all together. And there's the answer. Inch by inch, it's a cinch. Use your workbench on the side, okay? You got plenty of space in the margins to work out what you need to, and then bring it back into the project. Remember, every line, as you work up and down, should be equivalent to the one above and below it. We're training you for the Math Olympics, which is the next honors level. The next honors level, honors pre-cal. Woo, that's where most of y'all are heading. Some of you are heading to double dual, where the expectations are even greater. Okay. Any comments or questions on this? All right. So in addition to your assignment for 12.1, you have this due, and both of them are due not tomorrow, but Thursday morning. So you have the rest of the class today, which is 3 minutes. Yep. And you have advisory if you want. And then you got all day tomorrow in class. Juniors won't be here. Juniors, you got your blue book all squared away? Okay, good. All right. That's today's lesson.